Hello and welcome. This is the solution to practice quiz 1. So let's begin with the first question. What is the chemical symbol for potassium? That's of course just K. Moderate trick question here, maybe just trying to trick you and make sure that we don't confuse phosphorus, which has the symbol P, with potassium, which has the symbol K. Scientific notation for the number 0.00003405. So that's 3.405 times 10 to the scientific notation. The idea is to write our numbers with one digit, then a decimal point, times the appropriate exponent times 10 to the power. So times 10 to the 1, 2, 3, 4, 5. So we got to go 5 over. Sometimes you might think of it doing it this way. You might have to zoom in a little to really be able to count it carefully. But we have to move that decimal place over 5 times, so it's 3.405 times 10 to the minus 5. The density of mercury is 13.6 grams per milliliter. What is the volume of 100 grams of mercury? Well, we want the milliliters, so we start with what we're looking for. It's a convenient way to begin a dimensional analysis problem. Now we can begin with perhaps 100 grams and then multiply by the inverted density. Why do we invert the density? Well, I want 13.6 grams on the bottom per milliliter on the top. I'm just using my density as a conversion factor so that I can use dimensional analysis, grams and grams canceling, leaving behind milliliters. Now, if for some reason this breaks down, like let's say we get the unit we're looking for but on the wrong side, then maybe we just need to invert something and try the problem again. But this is easy enough here, just 100 divided by 13.6 is 7.35 milliliters. So 100 grams, not many milliliters because this is a very dense liquid. Mercury is one of the most dense elements on the periodic table. Of course, it's also noteworthy of being only one of 2 elements that are a liquid in their natural state at room temperature. Mercury is a metallic substance that happens to be a liquid, and bromine is a non-metallic substance that also happens to be a liquid. No other elements in their natural states at room temperature are liquids. So given 1 inch is 2.54 centimeters exactly, that's an exact conversion, not rounded, and then 1 foot's 12 inches, that's also exact. How many cubic feet are there in 1.55 times 10 to the 5 cubic centimeters? Okay, so we have a foot cubed is what we're looking for. So number of cubic feet is what we're looking for. We can start with perhaps the quantity 1.55 times 10 to the plus 5 cubic centimeters. Now if we look at our conversion factors, we can see we have 2.54 centimeters per inch. And then, so 1 inch is 2.54 centimeters. And then we have 12 inches in 1 foot. It's another conversion. Now, what about the cubic unit? This isn't a cubic centimeter, is not 1 cubic inch. In fact, you may want to think about this for a second. How many cubic centimeters are there in 1 cubic inch? Well, just try to picture a cube. I'm not a very good artist, but I maybe can draw a good enough cube. And if each cube has a dimension of 1 inch, then the volume of the cube would be 1 times 1 times 1 inch. Now, if 1 inch is 2.54 centimeters, then 1 inch cubed, go back to the unit here of 1 inch cubed would be equal to 2.54 centimeters cubed. And that would be 1 cubed, inch cubed is equal to 2.54 cubed centimeters cubed. Now you could work the math out. It doesn't matter what the answer is to me in this problem. What I know is that I could sort of cube this whole conversion. And then it's true that 2.54 cubed centimeters cubed are in 1 cubed inch cubed. Now, of course, 1 cubed is just 1. So you could also say that 1 cubic inch is equal to 2.54 cubed centimeters cubed. Just like applying this now to a foot, if we have a foot by a foot by a foot, that'd be 12 inches by 12 inches by 12 inches. So 1 cubic foot would be 12 cubed inches cubed. So to solve this problem, all I need to do is take 1.55 e to the 5, or times 10 to the 5, divide by 2.54, raised to the power of 3. I usually think of that as the caret symbol. So we do caret to the 3. And then divide by 12 raised to the power of 3. So that works out to be 5.47 cubic feet. Running out of space here. But 5.47 cubic feet are in 1.55 times 10 to the 5 cubic centimeters. Now, it's not really that important for us to do these conversions in a chemistry class. It's not like we're routinely converting between cubic centimeters and cubic feet, but it's kind of like problem solving using the units and the conversion factors and applying the idea of cubing the conversion factors for a problem such as this one here. Okay, for number 5, we have a substance known to contain only carbon and oxygen. 5.5 gram sample contains only carbon and oxygen. Carbon makes up 35% of the mass of the sample, while the remainder is oxygen. So which of the following expressions demonstrates a mathematical procedure to determine the mass of oxygen in the sample using the proper order of operations? Okay, so 35% of the sample is carbon. That means 65% of the sample is oxygen. So 35% times 5.5 grams would be our carbon mass. 65% times 5.5 grams will be the oxygen mass. Now, you could sometimes do this in a calculator and it'll work it out for you correctly. Now, all the calculator is really doing is doing, 0.65 expressed as a fraction times 5.5 grams, yielding a mass of about 3.6 grams for the oxygen. The remaining mass would be that of the carbon. Now, the question is, well, in terms of an order of operations, what are we really doing here? Well, we're kind of saying that 100% of the sample is either carbon or oxygen. So 100 minus 35 is the percent that is oxygen. So that would be 65. Then we need to divide this by 100 to go to a fraction. So a fraction times 100% is the percentage. So 0.65 times 100, that's where we get 65% from. So we just need to divide by 100%. So we can then multiply that now as a fraction by the mass of 5.5 grams. And so now if you look at some of the options here, they're kind of putting the parentheses in the wrong spot. Now, one thing you could try to do is plug A, B, C, or D into a calculator and see the different values for the mass that you come up with. It's really interesting, and I think it's A, C, and D. What we end up coming up with are masses that are greater than 5.5 grams. So if the sample is only 5.5 grams, part of it's oxygen, that should be a mass that's less than 5.5 grams. So what we want to do is take 100 minus 35, that's 65, then divide by 100, then multiply by 5.5 grams. You can kind of see here that if you move and miss the parentheses here, that A is going to get the answer wrong. Likewise, C is wrong because we're just doing 100, then minus 35 divided by 100 times 5.5. So we're doing all this math and then subtracting that from 100. That's not correct. And likewise with D, we're doing 100 minus 35, but we divided 35 by 100 first. We forgot to put that extra parentheses in. So just thinking about order of operations, making sure we do our calculations correctly and thoughtfully will be very helpful in a class like this one. So a nice example early on to see the importance of the order of operations in solving a problem. Now number 6 was just ask, so the answer to this question is B is the correct way to write out the answer and the way to plug in the arithmetic to solve for the quantity of the mass that is oxygen in the sample. And then number 6 asks for us to actually do the problem to solve for the mass, which we've already actually worked out right here, which works out to be about 3.6 grams. All right, so that concludes the video solutions for the first practice quiz. Thanks for the attention.